Imagine waking up tomorrow and looking outside your window. Everything seems completely normal. The sky is blue, the streets are quiet, and the earth beneath your feet feels exactly the same as it always has. But somewhere, deep beneath the surface, something impossible has happened. Earth is no longer an ordinary planet. The entire mass of our world has been compressed into a black hole. There is no explosion, no giant flash across the sky, no dramatic warning in the atmosphere. And perhaps the most terrifying part is this. From a distance, the Earth could still have the same gravitational influence it has today. But this would not last forever. The moment our planet became a black hole, the rules of our world would begin to change in ways that are almost impossible to imagine. To understand what would happen, we first need to understand something surprising about black holes. A black hole is not simply a giant cosmic vacuum cleaner that automatically sucks in everything around it. What makes a black hole so extreme is that an enormous amount of mass has been compressed into an incredibly small region of space. For an object with the mass of Earth, that region would be unbelievably tiny. If you could somehow compress the entire Earth without changing its total mass, the resulting black hole would have an event horizon only about 9 millimeters in radius. That is smaller than a marble. The entire planet, with all its oceans, mountains, cities, forests, and atmosphere, would be compressed into a region smaller than a coin. And once this happened, there would be no ordinary surface left for us to stand on. But here is where things become even stranger. If Earth suddenly became a black hole, while keeping exactly the same mass, the Moon would not immediately be pulled into it. The Moon would continue orbiting at roughly the same distance, because gravity at that distance depends on the amount of mass, not simply on whether that mass is a planet or a black hole. The same would be true for satellites in orbit around Earth. Their paths would initially remain almost unchanged. From the Moon's perspective, Earth would still have essentially the same gravitational pull. But there would be one enormous difference. There would no longer be a solid Earth underneath us. The planet that once supported life would have disappeared into an invisible region of space-time. Now imagine that you are standing where the Earth's surface used to be. In reality, this scenario cannot happen naturally because there is no known process capable of suddenly compressing Earth into such a tiny volume. But suppose, purely as a thought experiment, that it happened instantly. You would no longer be standing on a solid surface. You would be falling inward toward the black hole. And because the event horizon would be incredibly close to the center, you would cross it almost immediately. The event horizon is not a physical wall. You would not crash into anything when you crossed it. Instead, it is a boundary in space-time beyond which escaping the black hole becomes impossible. Once you pass that boundary, every possible future path would lead deeper inward. From the outside, however, the story would look very different. An observer far away would never simply watch you cross the event horizon in the ordinary way. As you approached it, the light carrying information about you would become increasingly delayed and increasingly stretched toward longer wavelengths. You would appear to slow down and fade, becoming harder and harder to see. But from your own perspective, assuming the black hole were large enough to avoid immediately destroying you through extreme tidal forces, you would continue falling across the horizon without experiencing a sudden cosmic barrier. The strange difference between these two perspectives comes from one of the deepest consequences of Einstein's theory of relativity. Time and space do not behave the same way for every observer. But there is a problem with our Earth-sized black hole. It would be extremely small, and that makes the environment near it incredibly violent. Gravity changes dramatically over very short distances. The difference in gravitational pull between your feet and your head could become enormous. This difference is called a tidal force. As you fell closer to the center, those forces would stretch objects along one direction while compressing them along another. This phenomenon is often described as spaghettification. For an Earth-mass black hole, these tidal forces would become destructive very close to the event horizon. So unlike the supermassive black holes found at the centers of galaxies, an Earth-mass black hole would be a particularly dangerous place to approach. And yet there is another fascinating consequence. If Earth became a black hole but nothing else changed, the moon could continue orbiting it. The sun would continue orbiting around the center of the solar system. The planets could continue along their paths, at least initially. There would be no magical gravitational explosion that suddenly dragged the entire solar system into the new black hole. But Earth itself would no longer be illuminated like a normal planet. There would be no surface reflecting sunlight back into space. From a distance, our world would become almost completely dark. Instead of seeing a blue planet surrounded by clouds, an observer would see a tiny, incredibly compact object whose most obvious feature would be the effect of its gravity on the space around it. For life on Earth, however, the situation would be catastrophic. Our atmosphere would no longer have a stable planetary surface beneath it. The oceans would not remain peaceful seas surrounding continents because there would be no continents. Everything that once made Earth recognizable would be falling toward the black hole. The atmosphere, the oceans, the buildings, the mountains, and every living thing would become part of the material collapsing inward. The world would no longer be a planet in the ordinary sense. It would become a region of space-time from which nothing could ultimately escape. But there is an important detail that makes this scenario even more fascinating. Becoming a black hole would not make Earth's gravity stronger everywhere instantly. At the distance of the moon, for example, the gravitational pull would remain almost the same because Earth's total mass had not changed. The difference would appear because all that mass had been compressed into such a tiny region. If you somehow remained far enough away, you could orbit the black hole just as you would have orbited Earth. The real danger would come when you approach the black hole itself. The closer you got, the more extreme the curvature of space-time would become. So what would the night sky look like? The answer would depend on where you were observing from. If you were far away, the former Earth would be almost invisible against the darkness of space. But its gravitational influence could reveal its presence. Stars behind it could appear distorted as their light traveled through curved space-time. This effect is called gravitational lensing. Light passing near the black hole would bend, potentially creating distorted or magnified images of objects behind it. In the right conditions, the black hole could reveal itself not by shining, but by changing the appearance of the universe behind it. And then there is the final destination, the singularity. According to classical general relativity, once matter passes inside the event horizon, it continues toward a region where the curvature of space-time becomes extreme. The equations predict a singularity, but this is also where our current understanding reaches its limits. Physicists do not yet have a complete theory combining general relativity with quantum mechanics that can fully describe what happens at such extreme conditions. So when we talk about the final fate of matter inside a black hole, we have to be honest. There are still profound mysteries hiding behind the event horizon. Perhaps the strangest part of this entire thought experiment is that Earth does not need to become bigger, heavier, or more massive to become a black hole. It would only need to become unbelievably compact. The mass of our entire planet could, in principle, fit inside a region smaller than a centimeter and create an event horizon. That simple fact reveals just how extreme black holes really are. They are not necessarily objects with infinite mass. They are objects where gravity becomes so concentrated that space-time itself forms a point of no return. Fortunately, you can breathe easily. Earth is not going to suddenly collapse into a black hole. There is no known mechanism capable of compressing our planet in this way, and nothing suggests that such an event is waiting to happen. The Earth will remain a planet, orbiting the sun, carrying its oceans, atmosphere, mountains, and life through space. But the thought experiment gives us something far more valuable than fear. It shows us how strange the universe becomes when matter is pushed to its limits, and how a planet that feels enormous to us could, under the laws of physics, be compressed into something smaller than the object sitting in your hand. So the next time you look at Earth from a photograph, remember what you are really looking at. A world containing oceans, mountains, cities, and billions of lives is also a massive collection of matter held together by gravity. Change the way that matter is distributed, compress it far enough, and the familiar world disappears. Not because its mass vanished, but because space-time itself would become a prison. And perhaps that is the most astonishing lesson of all. In our universe, size can be deceptive. Something as enormous as an entire planet can, under the right conditions, hide behind a boundary smaller than a marble.